Thank you so much. All right, so welcome to my talk on building petabyte-scale Postgres clusters. This is a specific project, and we'll talk about everything that goes into both the design of this as well as the trade-offs that come with big data generally. So I've been working with Postgres for 26 years, almost 27, and I've worked with it in a large number of capacities. I've worked as an application developer, as a database engineer. I've contributed one patch to Postgres that's been accepted so far. I serve on the Code of Conduct Committee, and on top of that, I have worked as an engineering manager, and I'm in the process of taking something that I had helped build at a previous employer and sort of re-engineer it in a more general way for the general public, in a way that isn't necessarily bad for them or for us or for anybody else. So we're going to talk about the original bagger from Adjust. We'll talk about their design, where it fell short, what we did when we started building the open source version, where we're at now, and the major trade-offs that happen here. One of the things that people typically assume is that when you're dealing with large amounts of data, you just need to choose the right technology and everything works. For us, that technology is Postgres, believe it or not. The thing that everybody doesn't understand is that once you have triple V problems, you know, volume, velocity, variety, that at some point you're just managing database internals anyway, and it's really important to choose database internals you can manage and to build your solution around those. So there is no such thing as perfect technology at these scales. It's all just a matter of trade-offs. So life before this, at Adjust, we had Elasticsearch, and Elasticsearch clusters of a petabyte or more. Anybody ever worked with a petabyte of data in Elasticsearch before here? Raise your hand if you have. All right. I've talked with Elasticsearch people, and typically they've never seen Elasticsearch clusters above 1.5 petabytes. And we had a petabyte of data in Elasticsearch, and it was on a 1 month retention. So that gives you an idea of how much data was coming in. At those velocities and volumes, Elasticsearch failed catastrophically. In fact, it failed so badly, we called it a very expensive dev null. You know, dev null being the device that you just pipe things to on the Linux kernel that basically discards them. That's basically what it was. We could write, but we couldn't read. It made the system totally unusable. We had a large number of problems with it. These included Java heap exceptions, which would happen from queries that requested too many rows. And then, of course, the Elastic client, being very helpful, would just rerun the query over and over and over again, eventually killing the entire cluster. The other problem was that Elasticsearch is has a very chatty protocol, and because of that, very large, high velocity, and high variety data sets actually don't do very well with it. For us, the answer to all these problems was Postgres. So specific problems that we had, I think I've mentioned most of these. Another one that we had was that, and this one's been fixed within the Java environment much more, but we had issues where stop the world events would pause Elasticsearch for 2 minutes, and that would cause a node to effectively leave the cluster. This would cause rebalancing, which would cause more garbage collection pressure, and if it wasn't addressed very quickly, in fact, what would happen is the whole cluster could be killed. So those were just some of the problems that we had. So the options that we looked at, we did a whole bunch of benchmarking. We looked at Cassandra. We looked at a whole bunch of other things. We ended up choosing Postgres because it had one of the lowest write amplifications that we came across in our benchmarks. We had basically a minimalist design inspired largely by MongoDB and Elasticsearch. And basically, the idea was to sacrifice everything else for just write scalability. So sacrifice read scalability because it's just log management, things like that. If you need, all of these things, every additional capability you need is a lot more that has to go into your design. But, for this particular case where it's just logs, application debug logs, having high write scalability and not worrying about read scalability made the most sense. So, basic idea here is data gets written to Kafka partitions. The topics are partitioned, and basically we read from a set of partitions and write to a set of Postgres databases. Very simple. That means the partitioning is totally random, or the sharding is totally random. It means our reads have to hit all nodes, but it means we can basically scale up writes by continuing to add nodes and basically repartitioning the Kafka topics. We had a C language routing trigger, and basically everything's JSON documents. And the cool thing is, unlike Elasticsearch, we don't have to index everything in the JSON-B. We can index the things we want to, and we can leave the rest out. Elasticsearch, on the other hand, insists on indexing everything. So we wanted to open source it. I got approval for it. I put time and effort into it, but the original version there was really built around adjust's use case, and it just didn't, it turned out to take a lot more work than we thought to make it generalizable and usable outside of their specific use case, right? And everything was basically statically defined as far as the partitioning structures. Making all of that dynamic was something that would have taken a lot of work, and that part we never quite got all the time on. So then I left Adjust. A few years passed. A few of us started to meet who previously worked at Adjust. And many of us already had experience with the system. We knew what it was capable of, and so we decided to design a similar system utilizing purely open source components, the ones which we had managed to have open sourced at Adjust, as well as writing our own. So that's basically where we started from. So our design strategy is basically as follows. We go with what we know, and the reason we do this is we want to make sure that our exposure to the things we don't know is as limited as possible. One of the things you start to find when you're working in very high velocity environments in particular, it's worse than volume, is that the kinds of things that you think you know that you don't can come back and bite you all the time. So starting with what you know so you can minimize the things you don't know that you don't know is really, really, really helpful there. So some of our design choices will be very surprising, but it's just because, hey, it's what we've known has worked in the past, and therefore we can have a baseline and we can test other things against it. If we don't start with what we know, then we don't even have a baseline, right? So here's what we started with. Many of you are probably looking and go, wait, Perl, really? But Perl was what was used for all the orchestration stuff at Adjust. It works pretty well. It's a very nice language if you know how to write it readably. And, but it is also a language like Scala, which if you don't bring your own discipline to, won't provide it for you and you'll end up with a mess. PGObject is a framework that I wrote, which basically allows you to take Perl object methods and just link them declaratively to database user-defined functions, and just simply say this, this object method is handled by this user-defined function. Moose is a postmodern object framework for Perl. It's very nice. And then basically from there we put as much logic in the database as we could. We still have the C language trigger, and basically the query proxy piece is written using Perl Dancer. We also added a etcd for cluster state management because beforehand, basically we would have all of the cluster state managed in certain Postgres databases. Everything would have to be listing there, and it just struck us that was a recipe for some additional problems. So we actually logically replicate changes to etcd, and then from there propagate the event stream for managing the cluster. So now let's talk about what the system actually looks like in its design. So here's the data flow. Data comes here from the service network into Kafka. Then we have these things called Shuffle. Shuffle is a multi-threaded data shovel. It is fully open source. We've already improved it significantly over a Just version. And basically the Shuffle will read from Kafka and it'll write to two different Postgres systems, sort of in a ring architecture, right? Then on the other side we have the front end, which talks to the query proxy, which will then effectively make queries to all nodes, or at least all nodes that are up, and if one node is down, it will read from the alternate that things were written to. Okay. And so basically, this allows us to, if we run into additional scalability problems, we can just add nodes, and as far as write scalability, we're never going to run into a problem. As far as read scalability, yeah, we don't get anything from adding nodes. So the controls superstructure is that we have these metadata servers which have Postgres on them, and they also effectively serve as the etcd servers. The query proxy talks to them, and before it makes the queries to the data nodes, and then we have an infrastructure as code framework that basically allows us to orchestrate the whole thing. So current status. And I know I'm running a little bit ahead of schedule, so I'll go back and not only, if we don't have a lot of questions, there are a few topics that I'll probably go into in a little more detail. Node control infrastructure is largely complete, although this is now being rethought in light of some changes we have on the C language trigger, which I'll mention in a moment. The metadata server schema functions are complete. We have the C language trigger in testing and a proof of concept done. We're currently using Postgres for metadata serving, but I'm not sure that that's always going to be the way we do things. We have a config for that done. The query proxy is what I'm working on right now, and we've actually decided to defer having an actual user interface until we have this part actually fully released. So we're happy for people to get involved on that. There are a couple things which have come up during the development that are probably worth talking about here. The first one is that we decided to use JSON pointers, okay, for determining which fields within the JSON-B we want to index, as well as which ones we want to actually do for partitioning. So we partition by time, and we also allow partitioning based upon arbitrary user-specified values pulled out of the JSON-B. So we're using JSON pointers for that, and basically we've had to write a data type for it. That data type then has different ways of, basically you can take a JSON-B and you can pass it to a function and say, I want the value from here as an integer, or I want the value from here as a text string. And that becomes very important for indexes, obviously, because your ordering for integers versus text is different, right? So that helps on the ordering side. The second thing is that the exact functionality within the C language trigger is possibly up for discussion. We haven't decided whether, if a partition doesn't exist, we've more or less decided that if a partition doesn't exist, we will now route the data to dead letter queues. But we haven't, but there's some other things in that area as well. So beyond GA, here are some things we want to address. And as I said, like some of our initial decisions are based upon trying to have a baseline based on what we know has actually worked. And it's worth noting that when I left at Just, we had 10 petabytes of data in this system. So Elasticsearch fell over, we built something else. It ended up being used more and more. We ended up with 10 petabytes of data in it, and we could only maintain a 14-day retention because we'd run out of storage. So that it gives you an idea of the velocities we were dealing with. I think that looks like hundreds of terabytes per day. So some of the things we want to change. So one of the possibilities is instead of having single Postgres servers, each of those groups could possibly be a Citus cluster. And if that was done well, maybe that would improve read scalability as well, so that you could still have linear write scalability by, say, having 4 node Citus clusters instead of each Postgres cluster. But we would need to benchmark that against a fully functional system. One of the problems that you run into when you're trying to do read scalability is that read scalability relies on being able to locate the record. And so because of that, you typically have a lot more overhead when you're writing and a lot more limitations to your write scalability. So it may be possible to get some of both by using this sort of just random sharding on one level, and then on another level having smaller clusters which do their own tuple routing. Another one is obviously the query proxy is written in Perl. That's not a very popular language, and frankly there are probably better languages out there for what should we use? C is probably not the right language for this. I think writing web services in C is something some of us have done. It's not something any of us like doing. Golang's pretty popular for that sort of thing. It's also something for this type of application I don't like working with that much. Java has its own nightmares, but we'll be looking at that and taking a look at different options. But since the specifications will all be open, it's also possible that people could write them in additional implementations however they'd like. So we have this question of scaling reads, and the question is how much do we need to scale reads? I think we'd probably have to wait until we have users that have specific requirements, and this will become clearer as we look at the trade-offs and some of the lessons that we take from this whole process. Right now we write twice. Would it be better to have replication instead? We don't do it right now because we are pretty sure we would overwhelm the streaming replication, the startup process. Right now Shelf basically will spin up a number of threads. Those threads will each load, I think, 2,000 tuples at a time via copy. And it's very, very easy to write fast enough that the startup process on the replica won't be able to keep up. So this last one is one that I actually think is actually pretty cool. Postgres blocks by default are 8K in size, and if you compile Postgres with a different block size, which is quite possible, it's a compile time option, the regression tests fail. Because there are regression tests that are really sensitive to things like cost changes and things like that, that are testing, does the planner make the right decision, and things like that. But when you start storing large JSON B blocks, it might make sense to have a 32K block, because that means that when you're actually retrieving these documents, you can do it with a single sequential scan rather than doing a sequential scan that gets all these toast pointers and then retrieving all the toast items one at a time over what's effectively a nested loop index scan, right? So this is something we want to benchmark, and if we do it, we will have to have our own regression tests, because we know that Postgres' regression tests fail in those cases. There are, of course, many more. A lot of things that I would like to play around with, including custom data types for the JSON B stuff and things like that. But these are probably the main and most highest priority ones. So I want to talk a little bit about trade-off lessons here. Scalability in one dimension is easy. It's really easy if you have almost no writes to scale your reads linearly forever, right? It's really easy if you have a fixed number of writes to scale your, if you have a fixed number of reads to scale your writes forever. The difficulties occur when you have to deal with trade-offs between read and write scalability, right? The second thing is, a lot of times people get into this and they think, oh, I know where the problems are. Right? One of the things I've learned in working in this field and is really important in this project is just benchmark everything. Right? And the reason for this is when you're dealing with high scales, high velocity data, you don't always know what's going to bite you. And when something does bite you, don't assume you know it, actually profile it, because chances are once you're above a certain level, your understanding of the system is totally incomplete, and consequently it will probably not be what you thought it was. So benchmark and profile everything always when you're pushing the limits like this. And then the final one is the whole specialization, generalization piece. There are general big data tools on Postgres. They do very well for certain kinds of workloads. Like the system here is absolutely not a transactional processing system. If you try to do transactional processing on it, you will fail miserably, right? Citus can do that, but if you try to store like this sort of massive log stuff in Citus, you'll run into write scaling limits that we don't run into, right? So what I usually say, and I think this is actually true, at least from the benchmarks that I've looked at when I was working on the original piece at Adjust, is that a well-applied specialized tool will usually beat a generalized tool by about 10 times. A poorly applied specialized tool will usually lose to a generalized tool by about the same ratio. So it's very, very, very important when you look at this to understand what's a specialized solution, what's a generalized solution, and where it makes sense, or where the technology actually fits your use case. Bonus learnings, absolutely different environment architectures for different needs. And as I said before, scaling in one dimension is easy. It's scaling in 2 or more dimensions that's really, 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 really difficult. And so as a result, it's really important to know your requirements, because if you don't know your requirements, you can't possibly choose technologies when you're pushing scale like this. And I want to kind of give an example of this multiple different environments for different needs, because one of the things which has come out of this project more recently is the fact that storing logs for 30 days or whatever is nice, but people also want to be able to do metrics on that, right? And if you do metrics on this infrastructure here, anybody think it's going to perform well? Right, it's not. So we're building an additional set of components specifically for doing long-term metrics generation out of these logs. And that infrastructure is just totally different. It's optimized around the metrics problem. So this is a shared storage solution. So basically all of your data comes through Kafka. It gets processed via Spark into Parquet files. It gets queried in Postgres in a way which allows us to take those Parquet files and merge them together, with LSM kinds of approaches and things like that. But that can then do the metrics and analytics piece, it doesn't do we need everything easily queryable from our logs piece at all, because of the fact that if you're going to just try to store large numbers of JSON blobs in Parquet, trying to store that in what's basically a columnar format not only doesn't give you any of the benefits that the columnar would give you, but it also basically makes it impossible to index anything you'd want to index. So that would actually fail just as badly in that case as this architecture does for the logs themselves. So I'd like to take questions. Here's where you can find the code repositories, as well as those for the other architectures that I was mentioning as well. We have a Parquet foreign data wrapper and some other things. Many of these were, again, forked from open source projects that we had worked on before. Are there any questions?